Right? There we go. We got the clap. All right. Welcome, everybody, to episode 3 of My Monastery Life. It's okay. It's okay. Oh, it looks extra wrinkly. It's okay. It's clean. Cleanliness is next to godliness, according to some people. Now, while folks are going to get in here right now, we're going to go over layout for anyone that wants to watch temporally in the future what we're going to be talking about today. So I have something, unless I didn't go back and actually edit my copy and paste from the previous episode, something about no true vacuum, question mark. Yes. Is that a thing? Because a lot of times when we say something like E, the speed of light. Yes, we say that. And then we do C. Oh, God, that's a terrible mark. Should probably get rid of that one. All right. So when we have our friend, the speed of light. Okay. When we say the speed of light, we write down C. And that is equal to the speed of light. Parenthesis in a vacuum. Okay. Now, that sounds fantastic, but it's the speed of light. It's the maximum speed that we, or at least to our knowledge, that something can go. Now, what is that thing? Not matter, because you would need to use apparently an infinite amount of energy to get matter. You can go like 0.9, 0.9, 0.9999999. But to get to the speed of light, that takes a lot. Now you say a vacuum. What is a vacuum? It's supposed to be nothing. Now, hold on. One step back, the actual speed of light. Okay, you shine a light into a water. It goes slower than 290, 2.9979. I always forget that it ends with like 458 times 8, tens of 8 meters per second. So, I don't know, 299 million ish kilometers per second, something like that. You go into water, it goes slower. Why? It's a more dense material. You got to go through. It's maybe being absorbed and then re-emitted by water and everything. And that's apparently one of the reasons why you put your hand in water. You start moving. It's like, wait a second. This or the pencil in the glass of water. You see, it's like, why does it look like it's over the side? Slight timing delay. I don't know. Maybe it's just a me problem. But now we say in a vacuum. What's that supposed to mean? It's supposed to be nothing. But there's actually something there because the laws of physics and everything start applying. Dr. Hassenfelder and I think it was closer to truth. I think it was probably Robert Lawrence Kuhn, I believe. Did like the 9 levels of nothing and everything. Okay, so at least physics works, at least math works in a vacuum, but also there appears to be an energy density. Professor Wolfram likes to think of it as the eames, if you would, which eames by their definition are pre-mimetic. Um, Basically, atoms of existence, atoms of space knitting together and everything. And that sounds like a very plausible argument. I have no idea whether it's true or not, but it sounds like a decent first level approximation, especially if we're coming to it from a more computational perspective in that particular regard. Now, it's it's also a crazy thing because when you do the sum of like all the energy, and if you were to define, let's say, an actual size to where we live, it ends up being a lot more than the estimated actual mass in the universe, or at least our realm of persistence. We'll say that, or the arena in which we live. Uh, Maybe we'll go into that calculation in a little bit. But okay, there seems to be some energy knitting together our reality itself. We're going to go into that. But first, join our friends in the chat, shall we? Rather than getting down on my knees, let me go over here and we'll do this little thing. All right. Oh, we got K-Shell, we've got Kali, and we've got the range. Good to see you, my friends. Good to see you. Thank you for joining. All right, Kali's commenting on compact. Now, I hear compact time. I'm not exactly sure what that means. Now, we're talking about like a minimum component of time, or maybe I should actually, let's just do the little Google. Compact Time. I feel like this is one of the, not timer, of course, trying to sell me those things along with my fat fingers. Okay. Okay. So it's in Google initially. Its AI overview comes up with an encoding scheme, a book, the short compact time short history of life on Earth by John C. Watson, compact atomic clocks. It's here we go. Let's just go into compactification. I feel it's going to collude theory and stuff. Hold on. Let's look at this together because we can learn together. At least I do better that way. All right. Theoretical physics compactification means changing a theory with respect to one of its space-time dimensions. Having a theory with a dimension being infinite won't change the theory, so this dimension has a finite length and may also be periodic. Okay, so that sounds uh like one could think of what time would be, and if you're going to set a limit there, you could have it as a Planck time. You could call it the Planck seconds. I like that term, Planck second. It communicates what it is, not a second. It's a Planck second. What does that mean? I don't know. I mean, see, that's the interesting thing with the Planck boundaries. Because a lot of times, somebody brought this up yesterday. We were thinking of them as kind of like a a minimum expression of something. It's a minimum unit of time. It's a minimal unit of length. That's how the heck we get that dang thing right there. Allegedly, again, I am very biased, and at least within the model that we got on the wall over there, I'd say we have plausible explanations for why. Um, we can get into that at some point, but we'll stick with. Actually, no, this might be a good place to jump off. Hold on, let me double check on whether it's a plus or minus sign. I'm pretty sure it's a plus side. Could be wrong. Okay, there we go. Yep, it's plus. Okay. See, convention matters. Convention matters. Especially if you're going to do things consistently. Otherwise, you end up with all these ad hoc little things. And I was listening to shout out to Kurt from the Theories of Everything channel. He sat down with like the head of the Harvard like physics department. I'm listening, and he has a title something like "There is no wave function." I'm like, all right, it's more clickbait and everything. I understand. You got to be provide. And he's going through, and the long story is I haven't finished it yet. If that's something you would like to check out, he just came out with it today. It's a good like 2 hour and 15 minute conversation. He's going through it. He's like, I was trying to find where the chasm was between like classical physics and quantum physics. And he's like, all right, I'm gonna keep on bringing them closer and closer together. And all the cameras over here. All right, closer and closer. And then I'm gonna see a point where we need to jump. And he's like, what the heck? So he ends up going into, I think, some of the key words for that conversation were non-Markovian processes, because a lot of times you hear about Markovian. Ultimately, it sounds like he's describing a very stochastic process. Now, again, I am a professionally trained physicist. I am not the head of the Harvard physics department. I'm a dude on the internet. As a dude on the internet, it kind of sounded like he said that quantum mechanics becomes less woo and just more, oh. The quote that I took away from it is, I've if this stuff pans out, he's like, I fear I've made quantum mechanics boring. Now I don't know what that means. I'm very biased. I think I might know what he's talking about. Basically, he says one does not necessarily need, like, the wave function is more of an emergent process rather than it necessarily being fundamental. Now, it's going to be very interesting if he sits down with Professor Sean Carroll. Shout out to Professor Carroll. There are also a lot of actual science folks are going over to the Blue app, the not the formerly Blue turn Black X app. They were going over to Blue Sky and stuff, and I could have sworn I made an account. I think I was like, there was a waiting period before I created like an account, and I feel like it got verified, and then I went to go find it, and apparently I didn't create it. So I'm over at Meme Destruction over on Blue Sky as well. So we'll see if it lasts. I know a lot of people like to migrate to different apps and then kind of tuckers out, but if it's a good conversation, I'm willing to have it. So as we're going through here, all right, so let's break apart C. And again, this is according to the monastery model that we have right here. And if there's one thing I've learned from trying to like go through the process with different folks, do I need more light? Let's see. Is that better or worse? Oh, that made it worse. Okay, there we go. But if there's, what the heck was I just talking about? Oh, if you're trying to demonstrate something to somebody, you want to do an example that they can do and not feel like they have to struggle. Because I remember even when I did a video on this, it took me so damn long. And why? Okay. Because what is C supposed to be? C is basically the speed of light in a vacuum, yada, yada, yada. Okay. So right now, what do we have it that equal to? Now, the general thought, and I've said this, and I'm happy to be wrong about this, it was minimum length. So the Planck length, that's divided by the minimum of time, E sub P, or the Planck time. All right, cool. Now, one of the things within the model that we're using over here at the monastery is we are utilizing the first step to do any of this, to be able to make these claims, is at least have conjectured, logarithmically closed forms for the 5 base units. So for the 5 base units, we have basically minimum of time, E sub P, Planck time, we got it right there. We got a minimum unit of space, or we express it as length. We square it, it would be area. If we cube it, it would be a volume. Cool. And then we got a minimum unit of charge, U sub P, Planck charge. You get a minimum unit of mass, M sub P, it's the Planck mass. Excuse me, a maximum mass. That's where I meant to go 5 minutes ago. And then we have a maximum expression of temperature. So that's capital T sub P Planck temperature. Now, when playing around with these things, and initially trying to replicate what Thad had been doing, I felt like I was going to lose my mind at some points. One, because I wasn't professionally trained in this stuff, so a lot of this stuff was new to me. Pardon. And that I also I would confuse the notation. I would see a TP and I'd be like plugging in like the Planck temperature and everything. I'm like, why is this not working? Because it was supposed to be lowercase t sub p there. Because both of them begin with T, but since temperature is a maximum, you use a big T, and since times at the minimum, it's lowercase. That's how I remember it in my head. Listen, you use whatever mnemonic that helps work for you. I need giant markers. Yes, that might make things different. Or make see, I need to learn how to. I had an iPad. I'm pretty sure the battery is dead, and iPads are very expensive. But I should probably get, if anybody knows of like a cool little side thing where I can just do like a standard blackboard or chalkboard or something. That would be cool. I know Professor Carroll had in his biggest ideas of the universe. He was using that, and it was such a beautiful program. It was an iPad program. I don't know. We'll see. Maybe I'll get one. All right. So yes. So basically, we have our Planck units here. So this is our dimensional ingredients. I just grok it simply as the stuff we're made of, aka our ingredients. Oh my God, I can't spell it all. All right, the stuff that we're made of. Okay, but here's the beautiful insight into all this is within the constants of nature, within the dimensional constants of nature, and some of them even being dimensionless. You only need these 5 ingredients. Now you'll see them in different forms. Like, see, this is speed. It's a speed. Speed is defined as length per unit of time. Length divided by time. Okay, I can do that. I can go into a calculator. I can go into Wolfram Alpha, Mathematica. Literally, just type in Planck length divided by Planck time, and it's going to spit out the speed of light, or at least to take like 5 to 7 digits, maybe it will be. Usually it's off by like 30,000 because these are only defined to 5 significant digits. We're going over a little bit about this the other day. And again, another side tangent is the reason why it's basically starts getting wonky at 7 digits. It's because something interesting is going over at our inversion boundary here. Little box with the hourglass there. And the claim is that there's something that goes on. And again, I need to dive a heck of a lot deeper into their literature. But when I start hearing like actual physicists and like people that have studied this, like, well, there's some digital mixing and stuff that happens at a particular energy. I'm like, what? We got some alchemy going on here. It kind of seems it's like because things can swap out just just the sheer fact it seems that I can do this and that's going to come up with something or a real close approximation to see itself, the speed of light. Why the heck does the math works? Oh well. He was it the unreasonable effectiveness of mathematics. I've heard some people say it's like, why does this even work? Maybe there are reasons why. Is math invented or discovered? Yes, I claim. But all right. So the interesting thing is, if you do this with our logarithmic closed forms over there, you're going to come out to C2, basically about 7 significant digits. Okay. But it's off. If you actually do the calculation, it's actually slightly greater than C. I think around the eighth digit or so, it's like a 3 6 or something like that. So it's actually a little greater. So how could that be? C is a limit. Well, the claim is at that 7 significant digit, something happens. All right. So we've got our stuff and it's doing our thing. What is the thing? Now, for at least me personally, this helps. I put a 1 in here. Why? It's doing one thing with this stuff. Okay. Just use that for notation, just because if you're going like h bar Planck's reduced constant, you would have a 2 pi factor in there. Why? Well, because it's a cycle. It's doing a circle type thing. Okay. Just with corresponding dimensional ingredients. All right. All right. So I got a 1 there. We got that. And we've got something going on. We call it the interaction, extended action. Exactly what it is, not exactly sure. We're calling it an inversion boundary. Some action, this constant is inverting upon itself, so it's going to maintain some balance. Is that a wave function? Is that some stochastic process? I don't know. That's for some really smart people that are watching now or temporally in the future to figure out. Or we'll just keep grinding away. All right. So for all these actions, we have another one of these guys. Literally 1. Yes, there's a 1 in there. Why? Because we're going to do a little offset here. We're going to do 1 plus. Now, the way we have it set up is there's going to be some form of a geometric action here, or something we can try to deduce about what the heck is going on. And we're going to have a combination of our j's. What the heck are the j's? That's basically from our hyperbolic partition equation, which we did the other day. It's 1 over x plus x cubed divided by 2 pi. So big twist, set that equal to I raised to the j, or I raised to the I. If it's easier, basically just an orthogonal twisting. And then that is all raised to negative pi divide by 2. So basically more of a little twist going the other way. And then we subtract out the Planck mass gap that we're currently claiming there. Is the gap a thing? I don't know. Is it very interesting that when you're taking a constant of nature and including it in a way to help derive the fine structure constant, or basically the actual claim would be, I'm just going to go to this will lead to, because it actually has four outputs. Outputs are the zhas, so we just represent them by the Cyrillic X's here. So, and we get four answers. Zh1, Zh2, Zh3, and Zh4. And then you can also view them as trigonometric arguments as well. And we square this guy, the first answer, we get alpha. We claim to all the known significant digits. And again, maybe this is off. Maybe it needs a factor of log 2 or divide by root 2. And then you get smack dab within the current experimental measures. Now, is that true? I don't know. Maybe there's a reason. We're thinking that, or at least me personally, I'm thinking if we do have some deviations in full disclosure, the closed logarithmic forms, they all have all the known significant digits within the error bars, with the exception of the Planck charge over here. Now, there's a deviation, and it just happens to start, I believe, on the 7th significant digit. Maybe the 6th, somewhere right in there. And again, is that an experimental thing? Does it depend? If we're only using elements that represent charge, are we really good? Is that why QED works so extremely well, quantum electrodynamics, and that we're able to measure things to like 14 significant digits? If we're only using expressions of charge, I think there might be a difference, or at least I read somewhere in the literature that there may be a difference if you're including something that has a mass component as well, or maybe it's a large mass component, maybe something within the interaction there. Again, we could just be wrong. It's okay. It's okay to be wrong. You just try to get better so we can try to level up, so to speak. Okay. Finish this and we'll get back to our friends in the chat. All right. So what the heck is this thing? The little hyperbolic partition equation. This is how we get the calculation. It's on the yellow shirt that I probably should have worn. I'll wear that tomorrow or something. Like I need to get some wrinkles out. But we have that. So it's going to be a geometric action, a combination of zhas, and then our inversion boundary. What is this that happens to get the speed of light as we have defined it to all 9 significant digits? Length divided by time. I'm putting the redundant 1 in there. First, just remember, or at least me, 1. We have a parenthesis. We're going to multiply it by 1 plus square root G I, the square root of the Gausskian constant, the minimal non-compact manifold, or 3-manifold. That's very interesting. Oh, it's also the volume of a idealized hyperbolic tetrahedra. And we multiply that by J1 minus J2. For those that have gone through the literature, J1, very small. J2 is like 3.66. It's a lot bigger. So you're having a minimum subtracted by a much larger, bulkier term, going by the square root of the minimum 3-manifold times our inversion boundary. Okay. And that will get you the speed of light to all 9 significant digits, and then we claim as many more digits as you would like. Because I think it goes like 3, 5, 8, and I think it's like 0, 9 or something like that. We got it on the website. I got it. I need to finish updating and going through and putting a lot more stuff on there. But okay, since we've gone through that, let's go back to our friends. What else have we got going on here? Oh, hey, Moira. Good to see you. Playing second link to a paper relates to entropy. The moment of computation. I almost thought you said the momentum of computation. Maybe that's even a thing too. Yeah, one of the things that I've learned from inversions that John Williamson and Rick DeWitt have been really stressing to me is that if you do one over something, you basically just get a different unit. So it's like if you're doing seconds, it's like, all right, 1 second, 2 second, 3 second, four, yada, yada, yada. If you were to invert that, it's just a frequency. It would be how many ticks are within each of those seconds. So if we want to, all right, let me get on that. Oh, that actually changes that. So let's go back over to our friend over here. We had Magnify, go to Wolfram, jump over here. All right, so if you have, for example, Planck time. So in natural units, you can just view this as one. That's why you can do all the dimensional analysis, and it's literally like magic. Okay, we have all these things. Oh, the definition, it's the square root of big G, the Newtonian gravitational constant, times h bar, the elementary unit of action, and that whole thing is divided by C5. C5. Wow. Speed of light to the fifth. All right. So we don't need to go into all the reasons. It gives this ridiculously small number, 5.391 times 10 to the negative 44 seconds. Okay. Done. So we're going to do some magic. One divide by the thing. Okay. One divide by the thing. The thing is the Planck time. This gives us, oh, the Planck frequency. What is that? 1.8549 times 10 to the 43 hertz. All right, that's just frequency per second. So basically, within each normal second, I view it as kind of like that many ticks of the clock, or the frequency of some oscillation, if you would. I don't know. It's, I guess in quantum field theory, they say it's like, listen, now don't worry about particles. They're just vibrations in the quantum fields, and everyone has its own oscillation, its own vibration. Whoa, that's cool. And then they never mention it again. I'm sure that's a lie. I'm sure that's a lie. I feel like that's how at least a lot of just, let's just say, internet observers like us take it. I'm sure there's a lot more involved there, and there are people that are out there that have all these different things because, for instance, each particle you can express as in the Compton wavelength. How the heck do you do that? Well, you go back to our old friend uh, Dr. Planck's little thing there. So he had the unit of action, so we'll bring that back up. All right, the elementary unit of action is normally h bar. You actually need the full cycle to compute what the Compton wavelength is. So rather than Planck's reduced constant or h bar, you do Planck's constant. And then you divide it, I believe it's by the mass. So let's do Planck mass, and then times c, speed of light. So it should give us out a length term, believe. Yep. All right. So what do we got here? Oh, 1.01 times 10 to the negative 30. What the heck does that mean? Oh, it's 2 pi Planck lengths. So basically, if you had a unit 1, it takes like a full circle to get around. Okay. So that's the Compton wavelength of something that would be the Planck mass if we were viewing it in some UFT type of thing, or at least that's what it sounds. Oh, so that's why it's, oh, because if you just do the Planck mass times c squared, you get Planck energy, blah blah blah. Okay, Planck energy. Now the interesting thing is, yes, it gives you its. We get more. Let's get in, I think, electron volts. Do we have electron volts here? Yes. All right. You get that 1.22 times 10 to the 28 electron volts. That's ginormous. Okay. The interesting thing is you would actually go with the Planck frequency. We do 1 over Planck time again and get frequency. What happens if we were to have a photon going at that frequency? Wait a second. That's a very large number there. What is that? Oh my God, we got 137. Note, that doesn't end up actually being 137. I hoped it was like 136 point like 8.5 or something like that. So um, I don't know. Maybe it's just wrong. Okay, so you get this number that is larger than that last number. This is the same magnitude. It just happens to have a 7 in front of it rather than a 1. You divide that whole thing by 2 pi, we should get down to, okay. Uh, okay, yeah. Basically, we get down to Planck energy again. Okay. I always get confused because I go from joules to electron volts, and there's a scaling factor and everything in there because of our nature of convention. But that seems to having to work. Oh, nerdy. Thank you for joining, my friend. Good to see you. So, okay, I've jumped around a lot. There's a lot of conjecture here, even if it lines up with the measurements and everything. Even if we have an actual explanation to why different things might be going on, um, doesn't mean it's right, but it provides an explanation. And to loop all the way back around to when I was talking about Kurt and the episode on theories of everything that he recently just uploaded today, sitting down with the head of the physics department over at Harvard, and they're talking, and it's like, yeah, basically when he brought things together, classical and quantum, it's like it just seems to work. Like it, from what I took away is one does not necessarily need the wave function to be the primal thing. It can simply be an emergent thing, and that a lot it basically it took a lot of the woo out of quantum mechanics. If what he's saying holds, and again, I haven't even finished the whole thing. I haven't gone through any of the literature. I've just listened to a couple of things he says. It's like, hold on, go back. What did he say? I mean, and again, this isn't not. You never know where a good idea may come from, but it's like when if you've got like the head of like a major university, whatever you think of Harvard or anything, like my dad went there, my mom went there, and everything. I stayed there for a reunion. I got really badly sunburned when I went to the beach. That's mostly what I remember. I was a wee memes then, but yeah, basically, you got the head of the Harvard physics department. He's like, I'm just kind of looking into these things and like this minimal literature. And then somebody a year before me, they basically literally used the exact same terminology describing a thing, saying it's an interesting observation, but they were coming upon it from more of just a mathematical viewpoint. And they never really extended into the quantum just because it's like, you don't do that. We know that this is the way it is. And then you start to think, I'm like, wait a second. I'm sure there'd never be a lot of groupthink. Not like a whole lot of people would be just saying things for so long and then just be like, that's how it is. Because yeah, come on. It's like plants love Brondo. Why? It's got electrolytes. It's what plants crave, man. That was a quote from, I believe, Idiocracy. Um, Something along those lines, probably single apostrophe for accuracy there. But I have no idea. And again, I am very biased. I am so biased on this because of what he said. If there's anything to that, I'm like, well, that makes interpreting a lot of the constants of nature that we have here, everything, a heck of a lot easier. Because it's like, what the heck? My best guess is what's the rate or the wave function? I'm like, and the only thing we really just have is the number of claimed arrangements for the exponential powers making up those logarithmic closed forms of the Planck constants here. We're just assuming you're arranging those in a particular way. Is that a wave function? I don't know. Is it a geometric action? Are they atoms of existence doing some, to observers like us, I don't know, a hypercomputation or something? I have no idea. I'm out of my league on that. That's why I need to drink more coffee. Clear the throat a bit. All right. All right. So, nerdy, you're going to have to show me how to do some animations or some stable diffusions to try to. We really want to learn how to use. Okay, this is just a me problem. I need to learn how to use Manum and do all those other crazy 3 blue plus 1 brown and just not even crazy, just the simple things. If I can get ChatGPT or an LLM or a agent like that to help me with it, I'm totally for that. But what we got now is, where was I going? Okay, let's just review Planck constants for just a second. Do I have a marker in my pocket? No. Oh, it's over here. There we go. All right. One could not tell. I occasionally get onto tangents and then another tangent and then another tangent. And I kind of loop around, but we're going to loop back here for right now. All right. So, Planck time, a minimal unit of time. So the claim is these are going to be the boundaries for a realm of persistence, the arena in what we live, or we colloquially refer to as universe. Um, I I tend to think universe, it does mean everything. If we're setting a boundary condition, um, beyond that, there be dragons. I don't know. Okay, so Planck units. The Planck time is a minimal unit of time. Planck length is a minimal unit of length. Now, we also get interesting here at the Planck charge because, to my knowledge, it's a maximal expression of charge. Because basically, if you take the Planck charge we have here and you multiply it by J1, that we're claiming that squared was colloquially referred to as a fine structure constant. Apparently, Professor Feynman preferred to remember it as its amplitude of the fine structure constant, or that 0.085, yada, yada, yada. You multiply J1 by the maximal expression of charge, and it gives you the elementary charge. What the heck am I talking about? Because now, put a little of that over there, you got J1, you multiply it by Planck charge, and then you get E, elementary charge. Elementary charge. I know it sounds kind of whimsical there. All right, why am I saying elementary charge and not just the charge of the electron? Because it could be the charge of the proton. It's just, to be fair, if you just do minus charge of the electron, according to our convention, it's just a normal elementary charge. No, it's basically the charge of the proton. Why? Because maybe you can't have one without the other. I like that song. I like that song. I know. I'm a terrible, horrible, no good person. Yes, nerdy, I agree. Okay, nerdy has confirmed my biases. That's good enough for me. He's a very wise rodent slash picklekin, I claim. Now, yes, we just went into real deep lore, meeting certain interesting entities on the internet. Oh, God, it's a lot of fun. Okay, so now that I've bloviated, oh, yeah, I need to finish this. So, we're claiming these Planck units, they're boundaries. We got a minimum time, a minimum length, a maximum charge. The interesting thing is, we're also going to claim the Planck mass is a maximum. And you're like, it's a Planck unit. It's 10 to the negative 8. That's very small in kilograms. It's like, yes, you do realize the mass of the proton is like 10 to the negative 27. Unless you spend some time looking at these things, you're like, oh, it's a Planck. It's a minimum little thingy there. And you realize, all right, 10 to the 8, yeah, that's what is it? About the mass of like a mosquito egg or something like that. It's like, oh, mosquitoes are pretty small. I've never seen a mosquito egg, but that's something you could literally like look under like a microscope and be like, oh, I see that thing. It's a very small thing, but you can actually like conceptualize that as a unit of mass. Now, what if that unit of mass, let's just say, was stuffed into something around the Planck length, let's say precisely 2 Planck radii. Well, according to the Schwarzschild solution, so basically the whole non-rotating, just an idealized, whatever the heck that means, black hole, you would take that mosquito egg, keep on shrinking it down, probably like another 17 orders of magnitude or so. So, and each order of magnitude is 10. It's kind of, like the Richter scale. It's like, all right, if there's a 5.0 earthquake, okay, that'd be pretty big. 5.9 is crazy, and a 6 is like order of magnitude larger. And that's why, yeah. Um, Yes, maximum. Blank temperature, that's a lot easier. 10 to the 32 Kelvin. How hot is that? Very hot. In fact, that pretty much anything as we know it, as far as I understand, would just poof, gone, gone. Just vaporize. Like the vapor would be vaporized. It's everything would basically, as far as I understand, just be stripped to its constituent components, which the most basic component you can get to, in my opinion, is energy. What is pure energy? Photons. Why am I basing that on a claim? Well, if you got an antimatter and its normal constituent, because the interesting thing is you need its constituent. Before I thought I'm like, all right, we just get some matter, we get some antimatter, because antimatter also falls down. There's some people that seem to maybe like or not like some of that. It's okay. But the interesting thing is if you combine matter with antimatter, so like, all right, you get an electron, you get a positron. All right, they're basically everything's the same. One is negative charge, one is positive charge. You have them come together, they annihilate. What do you get? Let there be light from annihilation. God, that's so. Geez. All right. Number one, I'm going to hell, so I already know that. Uh, number Number two, I mean, that's fascinating. Now we could get into a cosmogenesis type story here. God, I should stop talking. The analogies and the it's getting hard to differentiate some of them. I realize some people don't like that. I do like some woo, or at least a great story. I love a good story. My second universal truth. Everyone loves a good story. Now, how does that story line up? It's trying to follow the evidence the best I can and everything. If it comes out with something interesting, cool, we can go with that. All right, where are we going now? Let's go to what we had titled it. No true vacuum. Question mark. Because I don't know. I'm sure it could exist somewhere, maybe, possibly. Don't know. Remember, science is seeking to be less ignorant. But as an ignorant person, I'm going to attempt to pursue. Okay, let me add a little bit of light here. I'm casting my own shadows and everything. Let's a little better, worse. Bueller. Oh, excuse me. Euler, Euler, Euler. All right, I said it 3 times. That should bother somebody. Why do I say this? Because apparently, when you read about one of the greatest mathematicians of all time, Leonard Euler, you pronounce it, or at least I did, Euler. And then you hear someone else saying, it's like, no, it's Euler. It's Euler. Yeah. And then you come across the clip, shout out to Casey, uh, where you have like the seventh generation or whatever descendant of Leonard Euler saying, yes, I am so and so of the house Euler. And it's like, oh my God, we were all right. Berenstain or Berenstein? I don't know. That those two tangents aside, we've spin orthogonally around. All right, what the heck are we talking about a vacuum here? Okay, because when you start looking at the vacuum energy density, all right, here's where we do the computer Dora thing for a moment here. Start into the he's according to Nerdy, they stared into the vacuum, and the vacuum stared back. Many things could be said about that. That may be a very true statement. I don't know. All right, we're going to go to our ah, you liar. Well, here's the thing. What do you say? Are you going to say, no, it's Euler? That dude obviously pronounced his own name wrong. Now, I could be wrong, but I just remember you're let's just say, okay, if Dude Man, now not the judge, if Dude Man was at a rave and it looked like he was, as some people would say, on something, and he said it a particular way where it sounded like it was sloshed, I'd say, okay, maybe Dubin was on something and he was sloshed. They were at a very fancy mathematics party. Even like the BBC documentary is introducing, yes, yes, Euler's descendant, and he's very proper. He's going by. It sounds just like a very generational. I don't want to just say bourgeoisie thing, but it's kind of a bougie thing where it's like we are of the house Euler and everything. And I'm like, what am I going to do? Tell pronouncing his name wrong. I'm still going to mess it up all the time, but that's a different subject. All right, let's get back to whether or not the vacuum is a thing. All right. So you can just go into Wolfram Alpha. You can look up all these other things too. So what do we have? Let's just say universe, energy, density. All right. Yes, you have to find the right magic words to line up sometimes to actually get it to work. Uh, then density. Again, I cannot spell. Wow, I still cannot spell. Okay. Universe mass density. No, that's not. Uh, is energy density. Did I do it right? Universe vacuum. See, I was going to explain. You need to use the right magic words to bring up the right thing. All right. And you can tell I'm a noob and probably shouldn't have listened to me because this is actually a rho lambda. I just thought it was p lambda, and I thought p lambda and rho lambda were the exact same thing. I thought it was defined as one positive energy, one negative energy, because apparently rho lambda is equal to negative p lambda, and that's one of the crazy coincidences or something like that. And there might be okay. So basically, you get 5 times 10 to the negative 10 joules per cubic meter. Don't worry, that shouldn't mean anything to anybody unless you've actually studied this at all. But basically, that is the amount of energy. A joule is a unit of energy per cubic meter. What's a cubic meter? Something like this, like cube. So, like if you had like a cubic centimeter, you would have 1 gram of water. If you had a cubic meter, you would have 1,000 kilograms of water. It's according to a convention and a particular density and vacuum energy, and even even Wolfram Alpha occasionally will come up with that as no, that's radiation density, but it's still using liters and cubic meters. Water is a fascinating thing. Okay. So originally, probably, I don't know, maybe a year or so ago, I was just playing around with inverse and stuff. Oh, yeah. And of course, we get the Planck force as a factor in here. Uh, okay. So we get this number 5. All right. 10 to the negative 10 joules per meter. All right. So what are some things that we have? We have ones. What is one of our ones? Well, the elementary unit of energy, or as we say, or perhaps the maximum unit of energy, if we're going to view the Planck mass as a maximum, which we're claiming. Okay. Yep, Planck mass times c squared, blah, 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 gives us all these joules. All right. So let's do that excuse me, per cubic meter. What do we get? Wait a second. Oh, oh, that's a lot more than what we had. We got like 18 orders of magnitude more than where we should be. Oops. Now, that doesn't work. Because I think this is also where you get, was it like 113, 120 orders of magnitude? Some people will say if you express it in Planck lengths between the vacuum energy density and what we assumed it would be, or something like it. Was it the crisis on Cosmo? I don't know. People have crises for all different types of things and use different words, but all we're going to do is just a little bit of an inversion. 1 over, we just add. And no need to retype that at all. So just when you do this, I'm like, wait a second. I did 1 over. Now, this is not in the correct dimensions. We should note that. But I'm like, wait a second. That was 5 times 10 to the negative 10. 5.1 times 10 to the negative 10. Oh, this is just in reciprocal joules. This is a joules upside down. What the heck does that mean? Now, I noticed that. I'm like, huh, that seems to be pretty close if we could get the right units in there to what it is. Now, we have to be fair because we need to go based upon measurements. And I should probably spend some more time, but is it vacuum energy density? All right. So I'll just go over to all right. The cosmological constant problem. That's what we're calling it. Or at least this is where I find the information that I did for the calculations. Blah 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 blah. Okay. Now again, interpretations can vary and everything. This is primarily just a calculation. All right. So estimated value. So basically, they're going by the different Hubble parameters and stuff. Uh, and basically, right now, it's approximately according to the 2015 measurements by Planck collaboration, according to our friends at Wikipedia here. Take it for what you like. The Rovac is 5.96 times 10 to the negative 27 kilograms per meter cube. Blah blah blah. All right. So in joules, it's actually 5.35 66 times 10 to the negative 10. And then in GeV, because we can use electron volts to measure just about everything or express energy in some form, 3.35 GeV. All right, cool. And they're going over different folks at different forms that they thought, and they were up by orders of magnitude. Some are better, some are worse, yada, yada, yada. Okay. So all we did, just go back. All right. So could there be a way for us to try to figure out what was going on? And we're going over some of the conjectured things for the Higgs about, well, what if we set it to 1 joule second and you come up with an answer that seems to be like a retroactive explanation because they've already kind of had measurements that come back right at that magnitude, or at least like 4 or 5 significant digits. Um, but we have confidence in at least three. It's good. All right. So what did I do? I'm like, well, what if I took the Planck mass and I multiplied it by the Higgs mass and I set it equal to like, I don't know, one something or another? It's like, well, it's I don't know. Let's see what happens. How did I go about this? All right. I'm gonna cheat because I already have these things all done out here. Where is that? Vacuum energy density. All right. So I'm just trying to figure out how I went through this again. All right. So we'll do this guy. I'm gonna use this to cheat a little bit. All right. Oh no, I don't need the whole dang thingy. All right. I'm not saying that this is the answer, but this is ultimately where we're going. All right. So here's here's the thing. So I was taking some geometric means. All right, so let's do Higgs mass. Higgs mass. All right. So what I was going to do is I was going to take Planck mass that we'd used earlier, and I was trying to verify the Higgs mass, but apparently it didn't give me the answer that I wanted. So, but it tantalized me and drew me into another direction. Where did it draw me? It drew me into basically. So I'm multiplying two masses together, so you get mass squared. So if we take that off, going to give you a mass squared term. What does that mean? It's like, I don't know. No, 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 no. Oh. See, it thinks I'm doing conversion. I actually need to put the multiplication in there. All right. Gives you math terms. It doesn't know what that is. No standard name quantities. Okay. But it's squared. So we can take its square root. I know. I know. It's so exciting. It's I was always so afraid of math, but now you got the thing that can just do most of the math for you. Just need to understand the right words and have an idea of what's actually going on. It doesn't hurt to actually be able to do it with pen and paper too. All right. So it gave me this. All right, that blah 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 blah. I'm like, I don't know what any of this stuff means. I might kind of know some of that stuff now, but this is what intrigued me. I would have had no idea that this was an actual thing had it not been for Wolframouth, because I'm not looking at these. It's approximately 6.3 relative mass equivalent of 1 joule. That gives you the 1 joule over here, about 10 to the negative 17. So I figured, I'm like, that's like 2 pi. That's about 2 pi. So I threw a 2 pi in there, and it still wasn't quite there and everything. So I'm like, wait a second. Maybe the Higgs mass is not what I'm looking for. It's what am I looking for? Well, I'm looking for something with kilograms so I can square root it out so it'll be in the right dimensions and everything. So we do the same thing as we did before. We solve for x kilograms. And since we're solving for x, we got to solve for something. We need some constant or something. So it said it was about 2 pi joules. So how about this? Joules in kilograms. How do we do that? So we just do joule. Since joule is a unit of energy, we divide it by c squared, and that'll give us our mass equivalent. Equals. Enter. Go. Wolfram alpha. All right. So what it's doing here, it's just giving us the mass equivalent. It's about 10 to the negative 17 or something like that. And gives us this answer. I'm like, wait a second. This answer right here, it's not quite. Oh, it was a little too big because we need this number here. That's what we're looking for. Okay. So how do we get to that number? Well, I played around a little bit, went through some different iterations, and ultimately, in order to get that, we need this construction. We found this is probably the more correct way to write it. It was let's do it this kilograms. We need a number 3 in there. It's a threefold. We do that geometric mean, but within our root expression, we divide by pi. Okay. So what do we get? Hold on. Are we solving for x? Speed of light. I is in. Let me put the. Let me put 3 over here. Maybe I confused it. Okay, I obviously did something wrong. Oh, at least this time it's doing right. Why? Okay, it gives us basically, long story short, is you get 3 Planck masses. I mean, you could have the 3 over there just because it's multiplication and stuff. So, all right, so 3 Planck masses. We're solving for the x thingy over here. We got that whole thing divided by pi, which seems to be very useful within physics and math and lots of stuff. So we got some curve going in here for the root kilograms. And to be fair, if you want to do energy density, you could just put meters cubed in here strictly for aesthetics. I'm just removing that. We get this number here. I'm like, wait a second, that number there, that 5.9566 times 10 to the negative 27. Okay, that was in kilograms. 5.96 times 10 to the negative 27. Not quite. To me, at least, it's suspiciously close. It's suspiciously close. And you can express this in Planck energy. So you do energy, and then you just do, let's do it in joules. So for joules, as we literally have it set equal to a joule, boom, to give us an answer in joules that we're looking for, 5.354 times 10 to the negative 10. All right. What do we got in joules for our little thingy here? 5.3566 times 10 to the negative 10. 5.3566. 5.354. Got a couple of significant digits there for something that we're trying to estimate based upon an enormous amount of data, all this other stuff. Might there be something going on with this little thing that we've got going on here? I don't know. So we're coming up on the hour mark, so we'll just write this thingy on the board for anybody to look at, pick through, find prettier forms, you get better measurements, data, or anything. Feel free to let me know. But I like doing it as Is it 1 joule? And you can do this in Wolfram Alpha if you want. In G E V. To express, because these are both energies. This is a lot of these. So you can just do this conversion. You set it equal to square root. You can literally just type it like this of 3 Planck energy. Oh, we're going to write there. We need to actually write it out. Planck energy. And then times a little star thingy. X GeV, GeV, and that whole thingy is divided by, boom. Oh, you need bigger brackets. There we go. Boom. All right. Pi looks horrible. All right, there we go. That's a little better. All right, so 1 joule in GeV equals the square root of 3 Planck energy times X GeV divided by pi. And at least the claim is that's going to give you the, is it the energy of the vacuum. Okay. Now, if you actually want your divide by meters cubed, you can divide by meters cubed, and that should give you rho vac. I mean, I just didn't put the meters in there strictly for aesthetic purposes, but you can do it too, and it will give you the right answers. Or at least the answers that I claim are some of the closed forms that maybe we're looking for. But all right, been going for over an hour. Hey, thank you all for joining. Again, trying these out at different times. Is this something you guys like? Going to be doing this on a more frequent and regular basis, probably just Monday through Friday, early to mid-afternoon, kind of East Coast time. Try to give a little bit more warning so more folks can feel free to pop in, give some comments, share some feedback, and happen to be aware we've had some correspondence before. Maybe have a few folks come up. So other than that, take care of yourselves, everybody, and have yourself a wonderful day. Peace out.